Right, guys, I'm gonna go a little faster, obviously, because we need to go faster. Okay, it's always us A2 naki সবগুলাই হয়. No, it's just you guys A2. It's bad luck, but don't worry, we're gonna take care of it, guys. Okay, so we talked about this, and we came up with. I'm going straight into this stuff. All right, no more goal photo. All right, we're gonna do this, and we're gonna take some extra time from you guys. We're gonna finish around say 20 minutes from now, and how as far as we can go. All right, so simple harmonic motion basically has these two specific pointers, and the two pointers we had were what? Number one, what was the first thing we saw? That the acceleration is proportional to the displacement from the equilibrium point. And the second thing we saw is the acceleration is always in the direction of the equilibrium point, right? So we show these two things in an equation. A is equal to minus omega square x, right? This can be shown using this equation. If you see any problems, comment right away. All right, let's keep going. So A is equal to minus omega squared x. This is basically this is the defining equation of simple harmonic motion. Why? Because as you can see from the equation, A is proportional to x, and number two, there's a constant and there's a minus. What the minus represents is basically all the acceleration is backwards, right, towards the equilibrium point. So basically, if it's a pendulum or a ball in a bowl or a mass moving up and down, the acceleration is always returning to the equilibrium point. It's like, when you're moving towards things, it's basically accelerating in a negative value. And when you're moving away from things, it's basically a positive acceleration. So that's point number one. Point number two, what we're going to do now is we're going to take an example of a specific type of motion, which is basically a mass on a spring, right? And we pull it down and then we release it so that it moves up and down, right? So we pull it down and we start the motion when it crosses the equilibrium point again. The graph you would get is this. This is basically a sine graph, right? So from the sine graph, one of the things we talked about yesterday actually, was we can figure out at time, say any time t, where exactly we are in terms of displacement, right? So if this is x, the maximum displacement is x naught, and the time is t. So how do you find this? Number one, you need to use the sine component itself. So how do you use the sine component? Basically, we write sine omega t. Right, what this shows is basically omega is a unit which is expressed in radian per second. And t is time in just seconds. So when we put these together, you end up getting radian. So you get sine in radian. So what happens is you basically find out the position of the cycle where t is showing. So at this time, it's basically at this point of the cycle. So multiplying sine omega t, doing that mathematical function gives you the displacement. However, there's one problem with this. This value goes up to a maximum of +1, right? Mm-hmm. And a lowest of -1. So in the actual motion, it's not necessarily going to be +1 and -1. It's going to be x naught and say minus x naught. We take that to be this point. So basically, say for example, this has a displacement of 5 centimeters. If it has a displacement of 5 centimeters, the issue is that 5 centimeters does not reflect that over there. So what we do is we multiply this function with the amplitude of the motion maximum value. So if this is x naught, then we can just write displacement at any given time t, x is equal to x naught sine omega t. So this is an equation for motion or displacement basically. So if we differentiate this, we can find an equation for velocity, because if we're differentiating in respect to t. So it's going to become what? It's going to be rate of change of displacement, or basically velocity, is equal to what? Guys, if we differentiate this, we get omega. We take the omega out because it's a coefficient. So it's going to become x naught omega cos omega t. Good job, Max. So, and what we're going to do now is we're going to draw another graph, all right? We're going to use a different color. We've gone too much into brown. Say, let's use red. So imagine the motion itself, right? So when it's crossing through the equilibrium point, the velocity is going to be really high. It's going to move up at a high speed. And then when it reaches, say, the highest point, it's going to stop. And then it's going to start moving down again, slowly from here, accelerating. And it's going to reach the highest speed when it's here again. And then it goes down and stops at the lowest point here. So 500 displacement, like you put a max to min. 5 centimeters is just from one direction, right? It's -5 in this direction and it's +5 in this direction. So yes, coming back to this. So basically it moves up and down, right? So the velocity is highest when it's passing through the equilibrium point. So another interesting thing that you can see is, if we do it here, is, do we have any pencils? Man, we've come so far in life now. We don't have pencils on the table anymore. Anyway, I'll just use this pen. Interesting thing is, if we differentiate this graph, I differentiate graphs a little differently. What I do is I call it slicing up the graph. So slicing it, basically, we see the gradient at different points, all right? So this is me just pulling off relative points, and then I'm going to use a different color to show the gradients. The gradient's high here, gradient's 0 here, gradient's maximum negative here, it's 0 again here, maximum positive 0, maximum negative 0, and then it's going up again. So yes, if I was to add in a bit more here, it would look something like this, right? So it's going to be like this. So something like this. So that basically shows the graph starts at the maximum positive value, and then here it drops down to 0. It becomes a maximum negative here, drops down to 0 here, maximum positive here. So let's start drawing this. So 0, maximum value to 0, to negative, to 0, maximum positive, 0, maximum negative, 0. So as you can see, if we directly differentiate this graph into this graph, we end up getting a cos graph, and because it's starting at 1, right? And another thing we're seeing is the equation itself. So the equation of this is obviously v is equal to x naught omega cos omega t. If we take this a step forward, if we take it a step further, what we're going to see is that, well, let's try this again. Let's differentiate it again. So what are you going to get, Maxwell, if we differentiate velocity again?
Negative sign.
But what do you get if you differentiate velocity?
Oh, acceleration.
Acceleration. If you differentiate with respect to time. So basically, del v by del t, right? So, or del x by del t again, right? So if we do that, what we get is v, rate of change of velocity becomes acceleration, is equal to, well, basically there's going to be a minus sign, so I'm going to pull the minus out first, minus, and then there's going to be a coefficient omega. I'm going to pull that out first too. So if we pull all of that out, what do we get? We get minus omega square x naught sine omega t, right? So that's basically the equation we get. And if we go along and draw a thing for this, an acceleration time graph. This was velocity, by the way, versus time, and this was displacement versus time. So if we draw an acceleration time graph, and we're going to do that thing again, the thing I love doing, slicing up the graph. So say I start slicing this, right? So I'm just pulling down relative points again from different positions, and we're going to use red to slice it. So here it's 0, it's maximum negative here, the gradient 0 is here, it's maximum positive here, 0 again here, maximum negative, 0, maximum positive. And then if you want, you can draw a couple of, like, you know, blah 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 variations of the gradient as you move along, right? So again, let's the differentiation of this. If we want to go and plot this, what do we get? This is going to start at 0, pretty much fine. This is maximum negative, so we're down here, and then this is 0 again, maximum positive up here, and 0 again here, maximum negative here, 0 again here, and maximum positive here. And if we plot a graph through these points that we've seen, yeah, it's, there we go, oh, a little smudge there, but yes, this is what we get. So what sort of graph is this, Maxadul? Minus sine graph, beautiful, and that's the equation we got. We're going to write it again because we can't see it here so well. It's going to become A is equal to minus omega squared x naught sine omega t.
It's nice.
The music?
No.
Oh yes, it is. So yes, that's basically what we get. So now the thing is that these equations or these graphs actually show how motion varies with time, and obviously the motion variation is sinusoidal. So if we go along with this, if we take this equation, and along with that, if we take this equation, x naught is equal to sine omega t, we'll end up getting something really interesting. So we said that a is equal to this, right? And we can say x is equal to x naught sine omega t, right? Mm-hmm. So what does this mean? This means you can, wherever you have x naught sine omega t, you can rewrite it with just x. So where else do you see that? You see it here, right? Let's use a red pen here again. So there we have x naught sine omega t, which means you can substitute this into this equation, and the equation becomes a is equal to, you guys see that? Minus omega squared x. Boom! We just got the equation that we got. let it go here. A is equal to minus omega square x. So yes, equations do not fall out of the sky. They actually do come from a lot of derivation, and this is one of those derivations. This will come in your A-level exams if you're giving A-level exams. And this is what you get. A is equal to minus omega square x. So this is basically the defining equation of simple harmonic motion. Now, let's move on and list down a few equations that we can come up with this. All right? So, what are the equations we've come up with so far? So, if we do a quick review of a few equations we talked about yesterday. Okay, yeah, give that to me. I'll just put it here. Okay, you can. So, first of all, we came across a variable which was omega. So, omega can be written as, what were the things? Theta by small t. Or you can write 2 pi by capital T. Capital T is your time period. Or you can also write 2 pi f, where f is the frequency of the oscillation. Number one. Number two, after omega, then we have the defining equation of simple harmonic motion. The defining equation of simple harmonic motion that we just said a few minutes ago is equal to A is equal to minus omega square x, right? So where omega is basically this omega, angular velocity, angular speed, and x is the displacement, right? There we go. Moving on. Then we have further equations that we came up with. For displacement, the first one we came up with x is equal to x naught sine omega t, right? That's omega, by the way, it's not w. And then we differentiated this and we got v is equal to x naught omega cos omega t. And then we differentiated that again and we got a is equal to minus x naught omega square sine omega t. You can write that as omega square x naught also. And we use these to derive and get this equation. All right. Other than that, an interesting thing. What would have happened if we started our graphs not from the 0 point? For example, the displacement graph here that we used, if we were to quickly draw a sketch of each one, this was this, right? This was this, and this was this. What if we were to start our motion from a different position, for example, the highest point? Then what would happen? Basically, what I mean is, what if our displacement graph was like this? That means it's no longer a sine equation, right? It becomes a cos equation. If it becomes a cos equation, then what do we get? The equation becomes x is equal to x naught cos omega t, right? Mm-hmm. And if you want to go and differentiate that, then you get v is equal to, let's draw the equations for it first. What's going to happen if you differentiate cos theta, Maqsadul?
Negative.
Minus sine. So you're going to get basically this. And so if you differentiate minus sine, what do you get?
Cos,
you get minus cos. So basically you're going to get this. So for each of these, if we try to write equations, then what are they going to be? V is equal to, what does it become? You tell me.
Negative sine.
Minus x naught omega sine omega t. And the acceleration becomes minus x naught omega square cos omega t. Interestingly, whichever equation you use, you end up getting the final defining equation to be exactly the same. It doesn't really matter. Moving on from that, we can come up with a few more equations. One of the equations we can come up with is Vmax, right? So when is the velocity going to be maximum? When cos omega t reaches its highest value, right? So if you do that, then what does it become? Vmax basically becomes cos omega t's highest value is basically 1. So you can write Vmax is equal to x naught omega. Really simple, straightforward. Another thing that we can do is say at any point of the displacement, say it's moving, it's a pendulum moving from side to side. You want to find out the velocity at a specific displacement x. Maximum displacement is x naught, obviously, and we want to find the velocity just here. So what do? You can have an equation for that too. V is equal to plus minus omega root over x naught square minus x square. That's right. And these are the major equations that we have. If we want to add in a few more equations, then one very simple thing you can do is you can take Vmax and use it to find the kinetic energy of the oscillation. And how would you do that? You basically take this, substitute it into half mv square, and as a result, the equation you would get is Ke of an oscillating system is equal to half m. are we gonna substitute this first? Okay, we can substitute that. That's gonna be half m x naught squared omega squared. There we go. That's one of the equations we have. And if you want to find the velocity at the kinetic energy at a specific velocity, then you basically substitute this entire thing in the value position of v. Simple as that. There's no point deriving that because it's pretty straightforward. So yes, these are the equations basically that most of us will have to work with. Other than that, we have a few more things left in oscillations. The few things that were left within oscillation is the concept of damping, right? And we also have the energy conversions in oscillation, and we also have the concept of resonance. So what we're going to do is we're going to talk about these tomorrow, right? It's going to be Friday night tomorrow. Please join us at 11 o'clock. Hopefully our internet connection is going to be better, and I would like you to also, as I've told the other batches, I'm going to tell you guys also again. Number one, a lot of people are asking us to find a way to notify them when our classes start. So the thing is that we can't do that directly, because the system that we're using, the page, doesn't allow us. But what you can do to get it is basically subscribe. You go into the messenger of the page and you ask to subscribe. Automatically, then what happens is our team will be able to notify you. Until you don't subscribe, we can't do it even if we want to. So subscribe to your specific group or session or batch, which is basically AS, O levels, and or A2. And after you do that, you'll be able to actually join and be notified before every class starts. And hopefully our team will be able to tell you exactly what's going to be the topic every day. That's point number one. And point number two that I've told all the other batches, I'd love to tell you too, is the fact that please pray for the people that passed away today in the fire. And also, as I've told the other batches also, if you guys can come up with ideas in which we can save people's lives and not make this happen again, then I would be more happy, more than welcome, more than happy to actually help you come up with an idea, figure it out, and actually make it a reality. I don't want to see people to die anymore, honestly. People do die, but not like this. So yes, these are our final points for today. Thank you guys for being patient and holding along with us when our internet went bad and everything. And also, yes, these are our final points. Good night, guys. It's been a long day, and I hope you guys have studied hard. We'll be back tomorrow with the rest of oscillations. Basically, we'll be talking about damping, we're going to be talking about energy conversions, and we're going to be talking about resonance, and a few other tidbits, maybe a bit of questions of oscillations also. All right then, guys. Good night. Take care. Loved doing classes with you, and it's fun, especially because of the felt tip pens. They look so nice. It's true, man. It's true. Anyway, guys, good night. And before you go to sleep, have a chocolate. Bye-bye.
Yes.
What?
Yes.
Death. Cook death. Cook death.
Bye.
Bye.